Okay, in this video lesson, we'll have an introduction to identities. Well, what is an identity? By definition, identity is an equation that is true for all values of the variable or variables for which the expressions in the equation are defined. Well, let's see what this says. Here's an equation. On each side, we have two separate expressions. On the left side, we have x squared minus y squared, which is our first expression. And on the right side, we have the sum of x and y times the difference of x and y. So what we're going to do is we're actually going to substitute different values for the variables, like the definition is saying. And so we'll first substitute values for x and y. We'll first substitute on the left side, and then we'll substitute on the right side. And if this is an identity, the value we get on the left should be the exact same as what we get on the right. So we'll start by substituting some values for x and y. We'll substitute -3 for x and +2 for y and see what happens. So when I substitute those values in, then I simplify. -3 squared is 9 and 2 squared is 4. When I simplify further, I just happen to get 5. Let's take those same two values and substitute it on the right side. When we substitute, the sum of -3 and 2 and the difference of -3 and 2. The sum is going to be -1, the difference -5, and when we multiply, we do get 5. So this is the first evidence that this equation is looking to be to fit the criteria of being an identity. Well, let's substitute a couple more pairs of numbers. Let's do 1 and -4. When I substitute it in, when we square 1 and when we square -4, we get 1 and 16. When we subtract them, we just happen to get -15. Substitute it into the right side, the sum of 1 and -4 happens to give us -3, and the difference gives us 5. And again, when we multiply, we get the exact same value as the left side. Again, evidence showing that this equation is looking to be an identity. A couple more times. -2 and -1. When we square both of these values, we get 4 minus 1, which gives us 3. On the right side, the sum of the -2 and -1 and the difference of -2 and -1. We first get -3, -1, multiply, we get 3. Next, we'll substitute 5 and 0. Just to illustrate, we're going to get the same phenomenon to occur. When we square the 5 and the 0, 25 minus 0 gives us the 25. When we find the sum and difference of 5 and 0, we get 5 and 5. Product 25. And one last pair, 2 and 4. When we substitute the 2 and the 4, we get 4 minus 16, which gives us -12. Right side, the sum of 2 and 4 and the difference of 2 and 4. We get 6 and -2, which in fact gives us the -12. So this is just to demonstrate what it means to be an identity. Now let's take it to the next level. Look at some other examples. 2 times the sum of x and 5 illustrates 2x plus 10. Many of you look at this and would say, hey, that's the distributive property. Another example, a plus b, b plus a. That's an example of the commutative property of addition. One more. The sum of x and y quantity squared will give us x squared plus 2xy plus y squared. Many of you might notice that to be a perfect square trinomial on the right side. Well, we've seen a bunch of examples of identities. Well, let's look at some that are not identities, just so that we don't make the presumption that all equations are identities. So the first example is 2x is equal to x plus 4. In an equation, if we happen to substitute 4 for x, we get 8 on the left side, 8 on the right, so it begins to look like an identity. But according to the definition, we should be able to substitute any value in. Well, let's substitute 7. 2 times 7 on the left and 7 plus 4. Left side is 14, right side 11. So this shows that the original problem, 2x is equal to x plus 4, does not fit the criteria for being an identity. Another example, The square root of x squared equals x. Well, if I substitute 3, when I square 3, I will get 9. Square root of 9 is 3. So it looks to be an identity for this one value. But if I substitute negative 3, when I square that negative 3, I get 9. Square root of 9 is still 3. So this shows that the original equation, the square root of x squared equals x, is not an identity. So now that we have an understanding of identities, let's transition it into trigonometric identities. So there is a very popular one, and so we'll look to create or discover a particular trigonometric identity. So instead of substituting values for x or y, because we're working with trigonometry, we'll substitute values for theta, an angle amount. And what we're going to do is take theta, we'll find the sine of that angle, and then we square it. We'll do the same thing, and you take the cosine of that same angle and square it. And see what happens when we add these two values together. So we'll just pick some random values for theta. The first one is pi over 6. Again, I'm using radians. So when I substitute, I first need to find the sine of pi over 6. Well, we'll go to our resource to remind us. Let's see, there it is. Sine of pi over 6 just happens to be 1/2. So when I substitute, 1/2 squared just happens to equal 1/4. Now let's do the same with cosine. Well, the cosine of pi over 6, the resource says radical 3 over 2. So let's substitute radical 3 over 2. When we square it, we just happen to get 3/4. Now what's in purple says take those two values and add them together. Let's see what happens. So when we add the 1/4 and the 3/4, we just happen to get 1. So it's hard to see if anything is peculiar that's happening. So we'll do it a few more times and see if we have some consistency. So I'll try pi over 2. So we're going to substitute and determine the sine of pi over 2. Let's remind ourselves. Let's see, there we are. Sine of pi over 2 is 1. So when I substitute 1 squared, we just happen to get 1. Now let's find the cosine pi over 2. Resource reminds us that cosine pi over 2 just happens to be 0. So when I substitute 0, I get 0. Now when I add these two values together, I happen to get 1. So we're beginning to see some pattern here. Let's try a few more. 5 pi over 4. So sine of 5 pi over 4, the resource tells us, let's see, negative radical 2 over 2. So when I substitute it in, square it, I just happen to get 1/2. Now let's find the cosine of that same theta. Let's see, resource tells us the same value, negative radical 2 over 2. So when I substitute that in, squared, we get 1/2. When we add these two values together, we happen to get 1. So we're beginning to see this pattern occur. A couple more values to substitute in, just to overemphasize. So let's go find the sine of 2 pi over 3. Resource says radical 3 over 2. So there's our radical 3 over 2. We'll square it, 3/4. Now let's find the cosine. Cosine of 2 pi over 3 just happens to be negative 1/2. When we square it, we get 1/4. And when we add these two together, again we get 1. So we're seeing that every time we add the answers from sine squared theta and cosine squared theta, we tend to always get 1. Let's do one more. Okay, let's take pi, see what we get here. Sine of pi squared. Well, let's remind ourselves, sine of pi just happens to be 0. So 0 squared is obviously 0. Now let's go find the cosine. Resource says negative 1. Alright, when we square negative 1, we just happen to get 1. So again, when we add these two values together, we do get 1. So we're beginning to see the traits of an identity while using trigonometric functions. So what we end up with is this expression. The left side was, well, in purple, we did the x sine theta squared. added at the cosine theta squared. And it looks like every time we add these two values together, we always get 1. So this is our first trigonometric identity. And it's called the Pythagorean identity. And it has all the characteristics of Pythagorean's theorem. So let's look a little closer at the evolution of the Pythagorean identity. Meaning, back in the day, you were first introduced to the Pythagorean theorem, which was our a squared plus b squared equals c squared. And it was used when we were working with a right triangle. We had sides labeled A, B, and C. And so now if we evolve this and place this triangle onto the Cartesian plane, and we identify this one point here, and we create a circle going through that point. And now what occurs is that our three variables, the b is now the x coordinate because we're on the horizontal axis. The a, the y, and the c is now r because it represents the radius of the circle. So now a squared plus b squared equals c squared transitions to x squared plus y squared equals r squared. And this is actually called the equation of a circle. And now we take it one step further and we define our circle to be the unit circle. So our 4 points, the first point, we can give coordinates 1, 0, 0, negative 1, negative 1, 0, 0, negative 1. And so now we know y was the same thing as our sine. The x coordinate we discovered was the cosine, and r was equal to 1. And so now we can transition from the equation of a circle. What was x is now cosine. There's the beginnings of our Pythagorean identity. And all we did, if I switch the cosine and sine around, there's the identity we discovered on the previous slide. And this was our Pythagorean identity. In the next video lesson, we'll begin to look a little closer at the Pythagorean identity.